Welcome. This is a more expository presentation, practicing technology. I want to show you 10 theorems in graph theory. They're very exciting and they show that graph theory is not just a strange subject, but it's actually related to many core topics in mathematics. When I was exposed to graph theory first in high school, I just saw in a library, in the high school library, I saw a book on graph theory. I found it was a very strange thing. It doesn't have many relations to mathematics, to the other mathematics, especially not calculus or algebra. But the relations are very, very close. All of the results which we are going to look at hold for any graph, any finite simple graph. I have you here two finite simple graphs, actually the same. I like the picture to the right very much, because what this illustrates is something which is kind of a little bit a strange thing. You know, when Euler was looking at graphs in a topological setting with the Königsberg problem, he was thinking about graphs not as one-dimensional simplicial complexes like in the second half of the 20th century. Actually, many graph theorists are proud of actually having one-dimensional objects and not doing, or two-dimensional in topological graph theory, but not higher. But if you are looking at the graph, it comes with a natural simplicial complex, which is the Whitney complex. And Whitney, by the way, was working both in the continuum and discrete in graph theory. He started with graph theory here at Harvard. And I have you here a graph which has one-dimensional components. It has also a two-dimensional component here. It has a three-dimensional component. So it doesn't really matter how high the dimensions are. Everything works. So if you have a complete graph with 5 points, then this is already a four-dimensional object. So this should be very quick. I tried to make kind of such summaries over the years, starting with 2012. Let me get started with the first theorem. It's a Gauss-Bonnet theorem. The version which I have put on the top, this is kind of the ultimate version, which I like very much because it's very, very natural. The simplex generating function encodes all the combinatorial data which you have. So for example, for this graph here, it's 1 plus, it always starts with 1, and then we have 3 vertices plus 3t, and then we have 3 edges plus 3t squared, and then there's 1 triangle plus t cubed. And then if you take 1 minus f evaluated at minus 1, that's the Euler characteristic. That's the number of vertices minus the number of edges plus the number of triangles minus the number of tetrahedra, etc. There are different ways how we can compute the Euler characteristic, and actually most of the theorems, you know, actually almost the whole part which I'm talking about here deals with Euler characteristic. There's a little bit of generalization here about Wu characteristic. What actually happens is that you can write down this f function from local f function from the unit spheres. So if you look at unit spheres, for example, when you look at this vertex here has a unit sphere which is a k2 and a k1. So there are 2 components here. So what you can do when you compute the curvature here, you can actually just look at the unit sphere. And there is a formula of Levitt which is actually equivalent to this. I just rewrote it in a more convenient way, which tells you that the Euler characteristic is just the sum of curvatures. So that's what it is in differential geometry. If you have a surface, I have you here a surface, and you are looking at the curvature at every point, and you add up all these curvatures, you get Euler characteristics. This is classical differential geometry. So you have a donut, so you have negative curvature here, so you have positive curvature here, maybe 0 curvature somewhere here. And then you can also deform it. Whatever you deform here, you will always have Euler characteristic. In this case, Euler characteristic 0. You discretize it and you build a graph on it, and you count up all the vertices minus the number of edges plus the number of faces. You always get 0. And for a sphere, you get always the Euler characteristic is always 2. Right? When you start to look at this as a face, then you have to say what the face is. So in this case it's clear because it's a Brouwer graph, you can clearly say what the face is. But if you have a 21-dimensional graph, or very complicated, doesn't even have to be a manifold, very complicated graph, what are the faces? So you have really difficulties with that, and that's what Lakatos was pointing out. So we have to be very, very clear. The Gauss-Bonnet theorem is actually equivalent to the Gauss-Bonnet-Chern theorem. Gauss-Bonnet-Chern is only for even-dimensional manifolds. It's not even for odd-dimensional manifolds there. The curvature is not even defined because it's a Pfaffian. So in this case, it's defined for any graph. And when I started with this, I was actually looking at manifolds, and I kind of went up dimension by dimension and looked what actually happens with the curvature. So I was writing down curvature formulas for any dimension until I saw a pattern, and then later saw that Leavitt already had kind of such a thing. But it's interesting because I saw that for odd-dimensional manifolds, or discrete manifolds, it was always 0. And that turned out to be a Dehn-Somerville relation, which later also was then explained by index expectation. I was actually developing this index expectation thing just because of that, to understand what happens for odd-dimensional manifolds. But that's this Gauss-Bonnet theorem. It's very nice. For example, here in this case, if you compute the curvatures, so the curvature is here 1/4, this is -1/4 and -1/6. So this part, total part, has curvature -1/2, and this part also has curvature -1/2. General, for any graph, you just write down the curvatures, and the proof is ridiculously simple, because what you do is when you define the Euler characteristic, what you have is you attach for weights 1 to the 0-dimensional part, weights -1 to the odd-dimensional parts. And when you do that and you take the 1 here, you leave that. When you push everything onto the 0-dimensional part, the 1-dimensional curvature here on that, you push onto the vertices, and this you push, the 2-dimensional parts you push also to the vertices, you divide by 3. And so on, so you get this Leavitt formula. And what happens in the continuum with Gauss-Bonnet-Chern is that what we see is the curvature at the point, and we don't see the curvatures on the higher dimensional parts. And for seeing the curvature on the higher dimensional parts, you need this sheaf theoretical thing. You need vector fields and stuff. You need differential forms. So that's why you need more gymnastics, more analysis. And that's in general true here of all these results. In the continuum, you essentially have the same insight, but you have just much more technical things to deal with. So that was part 1 on Gauss-Bonnet-Chern. So the second theorem is also a very nice theorem, Poincare-Hopf theorem. It's for vector fields on a manifold, and you look at the equilibria and you define an index if the equilibrium is isolated, right? If the vector field is nice and isolate, that's technical conditions which you have to be satisfied. Then it induces nearby, from a small sphere nearby, it induces a map onto the sphere. So it's a map from a sphere, d-1 sphere to d-1 sphere, which has a degree, and that degree is the index, which is an integer. And when you add up all these integers, you get the Euler characteristic. It's the best way to compute the Euler characteristic of a surface or manifold. You just produce a vector field which you understand, which you know the critical points, and then you compute the indices. These are the divisors. So the I, G, V, these are integers. These are divisors. So it's somehow kind of a little bit of algebraic geometry. It's also physics in some sense, because what we have when we look at particles, so the charges or they are actually divisors, right? Because you have integer values, or half integer values at points, located on points. And it's a very natural notion in algebraic geometry, because you, for example, can integrate differential equations using this, see how the divisors move. So that's very nice here. This theorem has first been looked at in 2 dimensions and then higher dimensions. Hopf was looking at in higher dimensions. I think I was the first who actually looked at it in the discrete at least in that generality. I think in 2 dimensions there were others. So the index is just the Euler characteristic, 1 minus the Euler characteristic of the stable sphere. So it really depends on the function what the indices are. Also, this theorem is very clearly just, if you look at the fine triangulation of a manifold and you look at the vector field. Actually, one way how I formulated this once is you look at the vector field directed graph. So you put the direction on every edge, and so that can be an arbitrary graph, so it doesn't have to be a surface or anything. And then you assume that that's irrotational, so that you cannot go in a closed loop on a triangle and always in the same direction. So what you have is then 1 minus the Euler characteristic of the stable sphere, so all the vertices which come to a given vertex. So that Euler characteristic, 1 minus that Euler characteristic gives you the index. And it's also very clear what actually happens. If you look at the proof, what happens is you again look at the Euler characteristic. If you look at the Euler characteristic, which is just supercounting the weights on different parts, 0-dimensional, 1-dimensional, 2-dimensional, 3-dimensional parts of space. And so what you do is you have a function, and this function tells you, or kind of if you have an irrotational d-graph, it gives an order on every simplex. So you can especially say what the minimal part is. So you can say, for example, if the function value is smaller here, so you push everything, this weight here, you push here. If you have a triangle, you push all the thing to the minimum. So instead of distributing it equally to every neighbor, right, which gives you the curvature, you put it directly just to the minimum. So it's kind of like a direction. So it's kind of like a particle moving and not a wave moving in all directions. So it's kind of a very physical also. So that's kind of curvature is kind of when you take all these things together, you don't look at the function. So this depends on the function here. This is some functional vector field. In this case, it's a gradient field, but you can also look at the vector field version. So that's number 2. That's Poincare-Hopf. Now the third theorem is very nice. It's a very classical topic. It started kind of, you see, Blaschke. Blaschke was the PhD advisor of Chern. Chern was the PhD advisor of Banchoff, and so on. So you have this kind of tradition of integral geometry. Integral geometry is kind of a little bit a strange thing at first, that you look at probability spaces of things. For example, you have that the Crofton formula was one of the things, like the Buffon needle thing was one of the original things. So you have a curve, and you take random planes, and you look what is the expectation value of the number of hits, and that's proportional to the length. So it's something very natural also for curvature. When you look at curvature, when you look at these indices are divisors, and you take these divisors and you average them over a probability space of functions. Of course, it gives you the Euler characteristic, because what you have is, for each function you have the Euler characteristic, and you just average it, so you get also the Euler characteristic. It's something almost obvious, but it's kind of cool that you get here, if you take kind of a natural probability space like IID random variables on the vertices, then almost all functions are colorings. So you actually need here that the functions are colorings always. So that was kind of mentioned here. So the functions are colorings, meaning that different vertices have different, adjacent vertices have this different function values. In that case, almost all functions are really colorings, and if you average, you get this Leavitt curvature, which kind of just distributes the values of these charges, this omega x, which is charge, positive on even dimensional, negative on odd dimensional. It kind of just distributes it equally. There was a version where I look at all colorings. You average over all possible colorings with the chromatic number. But it's very nice, and actually this is also the key to understand why this curvature is really the real deal, why it's Gauss-Bonnet Chern in the. So if you have a manifold in a Riemannian manifold, a general Riemannian compact Riemannian manifold, and you place it into a Euclidean space, that can be done isometrically by Nash embedding theorem, and then what you have a very natural probability space of functions, which are all the functions which are linear in this ambient space, so linear functions. So when you look at the linear function, so this would be have index 1, this would have index 1. So for this function, when you take such a linear function, in this case would have just 2 indices 1. In this case, when you take a linear function, you have index 1, index minus 1, minus 1, 1. So you have this kind of very generic picture of a Morse function. Almost all functions are Morse functions, and so they have indices, and you can write down the indices. And now you turn over all possible linear functions, and you average over all possible linear functions, and then you get, by general principles, you get just the Gauss-Bonnet chain integrand. There is only one, so which is rotationally symmetric. So that's very, very, very nice. So you actually know that in the continuum you get the Gauss-Bonnet chain. So it's kind of surprising that in the continuums you have such a hard time to prove it. By the way, also these early proofs here, Allendorfer, so they first assumed that the manifold can be embedded into a high-dimensional space. So there was no Nash embedding theorem, so at that point it was not yet the full theorem. But Chern gave this proof, which is intrinsic, it doesn't need an embedding into a high-dimensional space. So that was this index expectation thing. I'm very excited about this integral geometry because it is kind of the key also to deform curvatures. So it's kind of, you can put some Riemannian structure on by just changing the probability space. When you change the probability space, you change the curvatures. So that's a way how you can modify, this is otherwise looks very rigid, but you would have to kind of generalize it. You can, by the way, all these things can be generalized when you have weights on the simplices, different weights. I call this energized. These are energized versions. So number 4 is actually, I don't think there is anything new since Poincare when you look at the discrete. So when you look at the original kind of, the original theorems of Stokes, fundamental theorem of line integral, Green, Stokes, Gauss, these theorems which you have in calculus. So we usually fight the whole semester until we get there, and it's kind of a hard thing. In the discrete, it's almost obvious. So you don't have to prove anything because everything is already there. So what you have is differential forms are just functions on the simplices. So you order the simplices in an arbitrary way. It doesn't have to be an oriented manifold, oriented graph. You don't have to be able to orient it in a compatible way. But then what you have is you have zero forms. These are functions on the vertices. You have one forms on these oriented edges. So how they are oriented is just a basis in your a space of differential forms. One forms, and then you have functions on the triangles. These are two forms. So you can put light. You can look at the Maxwell equations on any graph. Once you have an exterior derivative, and then you have the triangles, and then you have on simplices, three-dimensional parts, you have also functions. And so these are two forms, three forms, then two forms are on triangles, and so on. So and then what you do is you define what the exterior derivative is. So to do that, what you do is you first define what the boundary of a simplex is. So this is a 2 simplex, and the boundary is then just with some orientation. This gives you an oriented chain of 1 simplices. This simplex plus this simplex plus this. What you do is when you take the exterior derivative of a function on the edges, this is just the function on the boundary of the triangle. So what you do is you just add up all the so the curl of a vector field, kind of a one form, is just when you add up all this, when you sum over all the boundary, you sum the function values. So that's what it is, and you can do that for any simplex, and then by adding things up, of course this is linear, by adding things up you get this. If the surface is nice, right? So if you have kind of a thing like this, so for example we build a 2-dimensional surface. So this is a 2-dimensional surface, and if the orientations are compatible, so if the surface or the if the graph is orientable, then what you have is you have a compatibility of this orientation with this orientation, and that part falls away. So the boundary is then just this part. And so when you add up the curl over these triangles, that's the same thing than adding up the function values along the oriented path. So that's Stokes' theorem, or Green's theorem. So we don't care actually whether it's embedded in a three-dimensional part, where it's Stokes' theorem, or whether it's flat, whether it's Green's theorem. This has been reinvented again and again and again, especially in the computer science literature. This discrete calculus things have been done since more than 100 years in the discrete. So that's very cool. So that's a calculus. Now for the next thing, all of this is actually kind of accessible before you have seen any calculus or linear algebra. For this, for number 5, Hodge-DeRham, one needs a little bit of linear algebra. 2-3 weeks of linear algebra you need to do. So usually put such things into homework. D is now the exterior derivative, but you look at it on all differential forms. So that's one matrix. D is one matrix. So what you have is this matrix looks usually like this. So we have the D. This is the D star, and then when you take D plus D star, you get the self-adjoint of symmetric matrix, which is a Dirac operator. When you take D squared, you get the Hodge Laplacian, which is a nice matrix. And so what happens is L looks like that, and you have no triangles. And so what you have is you have a block diagonal form. That's the Kirchhoff if grad, right? So this is a D star. This is the one form Laplace, but in general you have these blocks. You have, and depending on the dimension, you have D plus 1 blocks in D dimensions. And so what you can do is you can look at the kernel of these blocks. So the kernel of these blocks, this is B0. This is the number of connected components. That's the zeroth Betti number. So what I wrote you down here is the HK. HK is defined here. It's just the case cohomology group as defined by Betti and Poincare. And so what you have is this beautiful relation. The Dirac operator also came relatively late. I mean, in principle, Poincare could have defined it because Poincare already looked at the incidence matrices. Right? These are incidence matrices, so he in principle could have written down the Dirac operator. Atiyah once kind of pointed out that it is strange. So his advisor Hodge had just an office near Dirac, and so they didn't talk. And Atiyah is very happy that they didn't talk because they didn't really discover all these things, you know, the relations between the power of the Dirac operator and Hodge theory together to find, you know, to look at invariance. You can actually kind of compute the dimension of these Betti numbers, the dimension of these cohomology groups, of the case cohomology groups. You can just compute by looking at the nullity of these matrices. These are finite matrices. So to compute a basis of the cohomology group, that's just the harmonic forms. This is the kernel of LK. This is harmonic forms. You can just compute that. That's the kernel, right? That's built into computer algebra systems. So these kernels, you have about 6 lines of code, which gives you a basis for the cohomology of an arbitrary graph, arbitrary simplicity complex. So graph theory is really kind of more general even than the theory of simplicity complexes. If you don't belittle them as one-dimensional simplicity complex. That's very nice. And it's not that hard. So what you do is actually just a fundamental theorem of linear algebra. It needs the thing that D squared is equal to 0. So that means that the image of D is contained in the kernel of D. So that's the key. And then you have this Hodge decomposition, and then you can immediately see that the harmonic forms are really kind of representing you elements here in the, so they're in the kernel, but perpendicular to the image. That's this fundamental theorem of linear algebra as we learn it in linear algebra courses. So that's why very, very important. This duality, between being perpendicular, between the transpose and so on. These are transpose. These are just matrices. These are finite matrices. And so we don't have any technicalities. In the continuum, you have technicalities. So you have to kind of, you deal with differential operators. So you have to make sure that you look at the right function spaces, etc. Maybe somebody has looked at it before. I didn't find anything before. I really looked at this Dirac operator before. But it's something very, very strange. I would not be surprised if it would have been looked at before, because that's the same thing you do in the continuum. But that's not how Dirac looked at it, right? Dirac was actually building this up with his Dirac matrices. So he kind of had to build this Clifford structure. Clifford algebra is actually just differential forms with some different algebraic structure on it. Now the next thing is really absolutely key. It's a nice thing. It's the McKean-Singer. I learned it from a book of Barry Simon's Zeichenfröse, Kirschen Simon. I had to prepare for the Gauss-Bonnet theorem at one point, because I was slated as a course assistant to actually for a seminar, to help out with a seminar, but this seminar then didn't take place. But I actually kind of worked through that thing, and I learned a lot from this book. It's a very beautiful chapter on Patodi's proof of Gauss-Bonnet. And there is also a nice exposition about McKean-Singer, and also a very simple proof of McKean-Singer. So it's just this symmetry of the Dirac operator which kind of gives you. So what happens is this is a symmetry between spectra on even dimensional forms and odd dimensional forms. So what you have here, you have this is zero dimensional forms, these are one dimensional forms, and so on. That would go on, right? You would have two dimensional forms, three dimensional forms. And so what happens if you look at the non-zero spectrum? The zero spectrum is related to the harmonic form, so that's kind of where the Betti numbers come in. That's the kernel, but the non-zero eigenvalues on the even dimensional parts and on the odd dimensional parts are the same. So this is what one calls also supersymmetry. And you can say it like that, that this is the heat kernel. The supertrace of the heat kernel is the Euler characteristic. And the reason is it's because for t equal to 0, it's a supertrace of 1. Supertrace of 1 is by definition the Euler characteristic, right? So that's the number of, and you take 1, that's the number of, that's the length, the number of vertices minus the number of edges plus the number of triangles, etc. So for t equal to 0, that's clear. And then you kind of make a Taylor expansion, and you use the supertrace of L to the k is 0, because the non-zero eigenvalues have this pair up. So there's for a non-zero eigenvalue here, there's a non-zero eigenvalue here. This cancels away. So this shows that this is true. And that's absolutely a crucial identity, because once you have that with this heat kernel, you can prove a lot of things. For example, we can look at the next thing, which is the Euler-Poincare formula, which is an old formula from Euler. Has looked at it in the case of in the case of polyhedra, right? Icosahedra also, you have this thing. So you have 0 holes. So the Betti number there's no hole. So the Euler characteristic is, and then you have 0, 1 because of the 0-dimensional part, and 1 because of the 2-dimensional part. That's Poincare duality. So you have 2 minus 0, which is 2. So you have this beautiful formula which tells you that this Euler characteristic is actually just a cohomological property. So if you do, for example, homotopy deformations, that doesn't change the you can readily see it here that it doesn't change the Betti numbers, and then you have also the Euler characteristic doesn't change. So that's pretty cool. So that's a nice thing. But how do you prove this? So the best way to prove this is to use the heat flow. So look at the supertrace of e to the minus TL. So if you look at that, and then t is equal to 0, so you get that. And t goes to infinity, it washes away every eigenvalue, every spectral part which to positive eigenvalues, which means you actually, when you apply this heat flow, you actually go to the harmonic forms. So this shows that in the limit t goes to infinity, when you only have the harmonic forms, then you have the supertrace is nothing else than this alternating sum of Betti numbers. So it's very cool that you can really kind of understand this in a deformation way. You deform the structure using the heat flow. You let heat, you apply heat to the differential forms. And then you get here a t equal to infinity. You get this, and a t equal to 0. And by the way, that's the best way also to see that. That's also a one-line proof. Once you see that, what you do is, so that's kind of another topic. Okay, here this is a kind of a dynamical systems story. What you have is a graph, and you look at an endomorphism of the graph. So you have a map which maps every simplex into a simplex. So it doesn't have to be an automorphism. It's enough that you have an endomorphism. But for simplicity, one can assume it's an automorphism. For example, it could be here a rotation by. So what you have is you have that graph endomorphism. Then now you define something which is kind of a dynamical version of Euler characteristic. Instead of the supertrace of 1 on the cohomology, which is kind of this here, what you do is you take the supertrace of the map induced on the cohomology. So what you have is, very concretely, what you have is you have these kernels here, the kernels, and T induces a map on the kernels. And so this map can be written down as a matrix, and then you have a trace of in each block, and then you take the alternating sum. That's the supertrace. That's the Lefschetz number. So that Lefschetz number is the same thing that the sum over all simplices which are fixed by the map and the index of that. So in this case, if you cyclically rotate here, it's just one simplex which is fixed. And so you can compute now the index of this, which is it's omega x, which is in this case 1. The permutation on the 1-point set has index 1. So that's actually index is 1 here. So what actually happens is this cyclic rotation here has just the sum over all fixed point sets. The index of the fixed point sets is 1. So the Lefschetz number of a rotation by 1/5 here of this transformation has Lefschetz number 1. Now, this is also the supertrace on the cohomology. So in this case, there is only the zero-dimensional cohomology, right? There's no hole. The supertrace is 1 also. So you can kind of immediately see that works for that particular example. But what is nice about this is that if you have a space which is contractible, this cat graph has a symmetry. And so the symmetry is just flipping things around. And what are the fixed points? This is this simplex, this simplex, this simplex, and this simplex. If you add up all these simplices, you get the fixed point. You get 1. So Brouwer's fixed point theorem is nice. If you have something contractible, then this Lefschetz number automatically is 1. So you have at least an empty set here, because then the sum would be 0. So that's Brouwer's fixed point theory. So about the history, that's Brouwer in 1912. And in graph theory, it was first for one-dimensional complexes. It was considered by Nowakovsky, Rival, and I proved it in 2012. I did not prove it with the heat flow. So the heat flow is really the way to do that. It's very, very, very natural. The second last thing is this Wu characteristic, which generalizes the Euler characteristic. Euler characteristic is just the sum x omega x. And the Wu characteristic is more complex. So what you do is, when you look at the Wu characteristic, you look at all pairs of simplices which are adjacent. So in this case, for example, you look at this with this, this with that, this with that. So it's a huge sum, and you add up all these omega x, omega y. It's kind of like an Ising type, interaction part. This kind of is the analog of the Euler characteristic. And so what happens? Whatever you look at here has analogs. So there's a curvature, the same idea we have looked at before. What you do is you take this energy here, which is kind of for any pair, and you just push it to the zero-dimensional parts. So this formula is a little bit more complicated, but there's a Gauss-Bonnet formula. There's a Poincare-Hopf formula in the same way, where you just have a function and you push it just to the depending on where the function is becoming smaller. Weyl-Banchoff is also obvious because it's just averaging Poincare-Hopf and you get Gauss-Bonnet. Stokes-Cartan is also, you have just to write down an exterior derivative. You can now write down an exterior derivative. And it's very similar to what you do when you have a product space, but it's not a product space, so the cohomology is more involved and more complicated, and so there are more cohomology groups. It's quite interesting. Here that also works the same way. So once you have D, you have a Dirac operator. The proof of this is the same. So this is actually, when you look at that, so why is this equal to that? Ekman was probably the first who kind of just talked about it. McKean-Singer also, that's the same. The Dirac operator produces this symmetry going from, you have then from the even dimensional to the odd dimensional thing. If you apply D, you go from the even dimensional to odd dimensional thing. That's, by the way, that's just what you have here. It is more general framework where this is not necessary. These are not necessarily differential forms, so discrete differential forms. Just some arbitrary complex. There's some nice examples like the cylinder, and you look at the Möbius strip. They have the same, simplicial cohomology because they are homotopic. They are homotopic to a circle. So, but in this case, this cohomology is finer and allows you to distinguish these two spaces. It's no more homotopy invariant. That's kind of also. So there are some things which become more subtle here. And then the last thing is maybe more a little bit just a bracketing thing. When you look at, for me, Atiyah-Singer is still an enigma. I kind of especially understand this curvature part, which is a complicated expression. The essence is very simple. So what you have is you have this elliptic complex which maps you, and now you can look at the dimension of the kernel of D minus the dimension of the kernel of D star, which is into discrete because the rank of a matrix is the same than rank of the trans, the dimension of E minus the dimension of F. So that's not very kind of exciting here. So there is not in the continuum we have here more interesting properties. So that's what one calls, but still one calls this the analytic index, and you have a topological index, which is a sum over these curvatures. These curvatures are kind of defined by D, and then you have also an algebraic version, which is kind of showing this quantity is a cohomological quantity. Elliptic complex is something which is in the continuum. You have to define it using differential operators. And in this case, what we really need is just this McKean-Singer property. We need this symmetry. And once you have this symmetry, everything what we have actually talked here is going over. It's just a framework which is more general. At least that's kind of my understanding at the moment. I'm sure this can be pushed much more towards the situations which are closer to the hard things which you have, especially if you look then at Riemann-Roch. It's still an interesting thing to pursue what you can do here. But there are examples. I mean, this is an example here. This elliptic complex defined by this more general exterior derivative, and then you can also deform the exterior derivative using integrable systems, and that gives you other elliptic complexes. It's kind of, you don't really need that framework. So in this case, this is kind of in the discrete. This is still kind of essentially a void shell, so it has to be filled with more content and more examples of elliptic complexes which go beyond what one has here, especially then in the context of Riemann-Roch, which is also a nice theorem in graph theory. I think that's it for now.